Hello everyone, my name is Bokyung from Autodesk Research. Today I'm going to talk about our work titled as Socio-Spatial Comfort, using vision-based analysis to inform user-centered human building interactions. Space designs and physical layouts influence our daily experience. So space designers and architects have tried to evaluate their designs by predicting the resulting experiences like thermal comfort or visual comfort. However, how the layout shapes social comfort is an open question, even though it is important in office context. So the goal of this paper is to inform socio-spatial comfort for future office designs and human building interactions by reflecting on the collected occupancy behaviors in the existing office. We looked at how people occupy this space during social interactions at personal desk spaces, which are not used only for individual work but also for informal collaborations. We started with a formative study by observing informal collaborations in the office. The major insight was that socio-spatial comfort is a type of tacit knowledge that can be captured by embodied interactions of detailed kinematic movements over time. The way people socially occupy space was not based on efficiency. Instead, there are specific areas that people wanted to pass by or avoid during both the initialization stage and interaction stage of social interactions. Then we employed a computer vision-based approach to systematically analyze and visualize socio-spatial comfort using real-life evidences. So we video recorded the entire journey of desk visit interactions in the office for a month. We collected data from various work desk configurations such as desk layout, partitions, and walls. For indoor occupant localization, we used OpenPose to generate skeletons from the video. Then foot joints at each frame were calibrated and projected onto a 2D floor plan. For our data-driven analysis approach, we developed a socio-spatial analysis system to manage, annotate, and visualize a large-scale behavioral dataset. Users can play back the data using a timeline. The tool visualizes anonymized skeletons on the left and visualizes projected 2D foot positions on the right. Users can annotate data by clicking custom labels and by specifying relevant skeletons with additional occupant information. In this study, we used annotation to categorize the data by social interaction types and comfort-related behaviors like eye contacting or approaching. Then we implemented 4 types of visualization techniques to help analyzing collected socio-spatial dynamics. And all visualizations are based on the data filters such as desk configurations and the annotated labels. First is aggregated heat map, which shows the overview of socio-spatial territories. In our case, this technique was helpful for demonstrating hotspots and territory of each social behavior, such as making an eye contact or having a discussion. But this technique ignores the dynamic aspect of spatial movement. Second is expandable heat map, which shows the temporal dynamics and shape changes. The system automatically generates multiple layers of heat maps for each time interval. Third is path drawings, which shows the trajectories during the approach stage. This technique is important for analyzing physical movements that last for short periods of time, for example, the initialization stage of social interactions. Last is onion skinning. To take advantage of having embodied information aligning with footstep data, we implemented a method to show pose transitions at a given time step. Users can iterate between these visualizations freely using synchronized time and skeleton information. The combination of visualization results together with interviews reveal that the dynamic movements during social interactions contain rich insights in terms of preserving social comfort, and the representation of these variations could inform future space design solutions. Then we proposed 3 theoretical concepts to describe socio-spatial comfort, which are social buffer, privacy buffer, and varying proxemics, and explained how socio-spatial perceptual knowledge are correlated with space configurations leading to different buffer shapes. Privacy buffer is the area that people tend to avoid passing through, making their approach path different from an optimal one. Also, collected approach paths do not only illustrate the area that occupants wanted to avoid, but also the area that they want to pass by or stay at before initiating the social interaction. We call these zones as a social buffer zone. The concept of varying proxemics explains how social distances change over time and suggests the importance of geometry-based representation rather than fixed set of formation shapes or distance to reflect on this dynamic phenomena. More descriptions and reasonings for each concept are described in the paper in more detail. In conclusion, we made 3 main contributions. First, we introduced the term socio-spatial comfort and proposed 3 concepts to describe this notion using real-life datasets. This concept explains that socio-spatial comfort cannot be estimated simply by visibility-oriented privacy metrics or static proxemic distance. Rather, it is based on the correlational mapping between human social perceptions and microspatial zones, which can only be derived from the real data. Second, we propose a vision-based occupancy analysis system that supports analyzing social dynamics using kinematic skeletons and 4 spatio-temporal visualization techniques. Third, we discussed the implications of socio-spatial comfort in designing user-centered human-building interactions and open-source our footstep data for future researchers. Thank you for listening.